This is the third part of this lecture. Now, after we finish discussing the displaying numeric quantitative or basically not the quantitative, the categorical data. Now it's a time to display to show you how to display quantitative data. I'm sure you understand that the main handouts are already uploaded on LMS for all parts that I'm using today. So this is just a video to be associated with the video, so you can really make a connection when you look at the handouts. I mean, associated with the handouts. Okay, so one of the very important thing in the past, you can imagine 100 years ago or even further in the history, people were collecting data manually, obviously without any technology, and they wanted to represent or present their data in a way also to make an analysis. So they came up with similar idea, but definitely they didn't come with the similar. They came with the original idea on how to count data. So they came with the idea of stem and leaf display. You can see here on the right hand side of this picture on front of you some handwritten ways of representation of a data that looks like histogram that we know on the left hand side, but in a horizontal way. And not only that, in fact they are actually being presented using the original data. So this was in the past was used as a method to count and to see the distribution of data. And nowadays we are lucky enough to have this computer-based solutions to help us to represent this data, but in what we call it histogram. I'm going to show you very quick what means stem and leaf, and most of the current software not anymore showing any option to produce it, because it's only relevant when you have limited number of data points. But when you have hundreds, more than hundreds and thousands, and nowadays big data, you cannot use this at all. So that's why the stem and leaf from now on, guys, you understand this is only relevant and only possible if you have few data, could be 30 or 40 or even 50 maximum, because it's going to be handwritten or handwritten exercise. You cannot use computer to do it. But if you are interested to make a programming to do that, of course you can, but it's only for fun. But in reality, no one is using it because we are not anymore dealing with this extremely small data set. In fact, we are using this histogram on the left-hand side. I'm going to show you how we present, maybe I showed you before in another video, how we construct histogram, which will show us a couple of interesting things here. So let's continue with the discussion with the stem and leaf, just to give you an idea how we build it and how we construct it, just for your information, because it's unfair to everyone who developed this method in the past that we forget our past. We need always to appreciate what happened in the history, because they were the reason why we are here today and why we enjoying what we have today in terms of technology. So imagine that you have data like that, 21, 22, irrespective of what does mean, but in the end you can notice that the first step you need to do in order to construct stem and leaf is you have to sort them in ascending way. That means start with the lowest up to the highest. So if your data is shuffled and randomly collected, you need to sort them from minimum to maximum as you see in front of you. And then let me take a pen here just to give you some sort of understanding. So you can see here it's 2 digits each one here. So we might really say, okay, why not to take all the 20s in one group and the 30s in another group? And if we have 40 and more, we can take them in our group, and this is it. So for that reason, the 20 and the 30s and the 40s could represent the stem of a tree. So 2 and 3 and 4. So it's easy. Now let us see in the category of 2, the 20s, what do we have? We have 21, we have 22, and we have 24. 21, 22, and 24. You see there are three location here or spots for the 20s. What about the 30s? 30s have 4 spots. One is called 33, yeah, and another 33, and 36 and 38. You can see them here easily. 33 twice because we have 33 for this one and another 3 for the second 33, and then the 6 for the 36 and the 8 for the 38. As for the 40, you have only one. If you look at it here, it looks like, yeah, it's if we try to make it vertical like we usually interested in, if we put 2 here, 3 here, and 4 here, you can easily put here 1, 2, 3, 4, 1, 2, 4, I mean, and here 3, 3, 6, 8, so it will be a little bit higher for 1, and here it's only 1 here. So it looks again histogram, but or bar chart, basically vertical, but in fact this is horizontal way. So you can see the interesting thing is if I give you bar chart like that, you don't know what was the original data point each one, right? You don't know. You know that there is 1 here, there are 3 elements here, and there are 4 objects here, but you don't know exactly what was the you know they are in the 30s, but you don't know exactly who they are. But by using stem and leaf, I can reconstruct the data. So if you give me this, I know that this is the stem, okay, 2, and how many? I have 1, 2, 4, so I have the first one 21, then 2, 22, and 2, 24, and so on and so forth. So this is one of the interesting characteristics. If you have stem and leaf, you can always come back to the original data. But if you have histogram, you can't. It's impossible to know what was the raw data. So this is very important to know the difference. Okay, now let's definitely forget a little bit about stem and leaf, but don't forget how it's being calculated in order to appreciate the history. When you see this graph here in front of you, you see 2 histograms for 2 different data. On the left hand side, you can see that we have here a graph that has 2 peaks here. This is first peak and this is the second peak, very clear. We have 2 mode here. We call it bimodal because there are 2. If we have 3, another third one, we're going to call it trimodal, and if there are multiple, we're going to call them multiple model or multimodal, in fact, distribution. Immediately when you see something like that with, in this case, bimodal, you can expect your data could be segmented. So I can say, okay, that is, I have customer segment here and another customer segment here. So this could suggest that why not to have different products. So product A for this group of people and product B for these people as well. So that means if after you get your data and represent them in a histogram and you find out that there are 2 clear peaks here, then you immediately know that you have 2 segments here. And by looking at 2 segments, you immediately know that, oh, one product doesn't fit all our service, then why not to do it in like that? Okay. So if we have data like this one, it looks like most of the bars are really close to each other. They just vary in a very narrow space, but we call it, it's like all equally, all of them, they are equal. We call them uniform distribution here. So uniform distribution is very nice. It shows you that each point here has similar possibility to happen. But for histogram like this, it looks like this value here, it's the midpoint of this bar, is the highest possibility to happen in our data. So that means if this is, let us say 120, so we know that in our data 120 happened several times, and maybe here it's 80, something like that, then we know, or 85, we know that 80 was or happened multiple times here. In this case, all numbers happened in a similar way. So in each of things happening in our life, they have distribution like this. As you guys, you know, If you want to know how many times you were happy, how many times you were ups, how many times you were down, this is an histogram, this is distribution. Hopefully, um, the bar for happiness is higher than the bar of sad. But if you have both of them equals, then you have a uniform distribution of happiness and uh, and um, sadness. But we always hope that you will be in the bar of happiness is higher. The same for if you have another distribution, like let us say healthy or not healthy most of the days. So until maybe in the last couple of the last 6 months, number of days that you were healthy, this was your healthy, and the number of days that you were not healthy, they were like that. This is definitely, it's a good representation that is healthy and here not healthy. But if you have it other way around, that is not good, right? So again, distribution tells you in a very quick picture the situation in your business here. So let me go down here. Okay. So this is another distribution that shows you that it's a symmetric, which means if you take a line in the middle, you will have two types of two halves equal to each other, and this is what we call it symmetric distribution. And usually in grading system, we like very much to have normal distribution like this, or maybe symmetric distribution. That means the middle will be the average. So we have number of students who are less than the average equal the number of students who are higher than the average. This could really represent that there is a normality here, and this could be interesting. Of course, we hope the average is high, so even the lower than average is still a good grade. Otherwise, it will be not a good indication of the performance of the course. Um, Sometimes they are not symmetric like that. They are very shifted like this. Yeah, I tried really to build a graph like this. You can see shift here. Let me take here another pen here. So if you have a distribution like this one on the left hand side, the tail. So if you go up here, if you go up, usually the upper one, it looks like this one, right? So that means this symmetric, the right tail and left tail are almost equal. Hopefully, that's why we call it symmetric. But in this case, if you look at the tail here, the tail is really here longer to the left, so we call it left skewed because the tail is on the left, and the right one is really small, not equals the same here. On the other side here, we have different situation. It's the opposite. So this is the right skewed. This is very important to know the difference between right and left. So usually we call it right skewed and even positive skewed, and here we call it negative skewed. So that's the skewness. So sometimes if you see something called skewness, if it's negative, you know immediately that the distribution will look like this one, something like this. But if it's a positive, it will look like that. It's a right skewed, something like that. So they have meaning, of course, and you can really check later on what's the meaning of negative and positive skewed. Whether it's a good or bad, we don't know. It depends on what you are talking about. So for instance, if left-hand side represent grades of a course, of course is good. Why? Because most of the students got high grade. But if you look at the right-hand side here, if this is the grade, you can say that, oh, this is not good because basically most of the grades are less than the average. So in this case, the negative skewed is better than positive skewed. So if you change the variable, the meaning of skewness will change as well. So be careful on that. That's a very important concept. You need really to pay attention to it. This is another representation to know what is skewness, what's kurtosis. Here it's how the kurtosis is. In skewness, you can see the mean is all on the left-hand side, left skewed, negative skewed, so you can see it very clearly here, the difference. So, but also you need to pay attention to the position of mean versus the median. If it's left skewed, the mean is less than the median, but if you look at the right skewed, it's the other way around, the mean is higher than the median. So it's very important to know that the skewness. If I go here to another representation of kurtosis. So you can see kurtosis, it means the peak. If it's a positive kurtosis, then the peak very clear here. but if it's a negative kurtosis, it will be flat. So you cannot see clearly any peak. So when you see peak, very clear peak in your distribution of data, you know that the data has positive kurtosis. But if the peak is not clear and you have multiple multiple columns that they are more or less similar to each other, like uniform in the middle, then you know that is a negative negative kurtosis. Platycortic, it means flat. Leptocortic, it means peak or positive. And there is normal distribution. It's something in between. It's called mesocortic, something in between the leptocortic and platycortic. It's very important to know the difference. And once you tell me that that distribution is positive kurtosis, I know immediately that is even that has a peak. So basically, if as a question here, if someone tell me, hey, the skewness of my data, it's a negative and the kurtosis is positive, okay? So immediately I can imagine immediately how it looks. Negative, it means it has a peak it has a tail on the left hand side, and positive kurtosis means there is a peak somewhere. So it looks like this one, because it's positive, because it's a high kurtosis, positive kurtosis, and then it's a tail on the left because it's a negative skewness. So the distribution will look like this. So now you can understand and even reconstruct your distribution based on the knowledge that you get from skewness and kurtosis. So it's a very important concept. I wish really guys to really pay attention to this. So let me see what's next here to show you. Yeah, this will be the next video here. So I'm going to stop here, and the next video I'm going to talk about the calculation of some of the important statistical concepts and to differentiate between the arithmetic mean and the geometric mean.